plane is traveling with an airspeed of 40 knots with a bearing of south 20 degrees east, encounters a wind of 50 knots acting with a bearing and direction of south 30 degrees west. Rounding to the nearest whole unit, we want to express the velocity of the plane in terms of I of j, express the velocity of the wind in terms of I and j, and find the true speed and bearing of the plane. Let's draw a picture first to show what's happening. First of all, we see the plane traveling south 20 degrees east. So we're going down and to the right, and the angle with relation to the north-south line is 20 degrees. And then the plane encounters wind acting south 30 degrees west. So when the plane encounters that, we have a new coordinate system drawn, and from the north-south line of the dotted red line, it's 30 degrees down and to the left. We do know that the plane was traveling at 400 knots. We also know that the wind was traveling at 50 knots. We want to express the velocity of the plane in terms of I and j in the air. That vector of the plane is going to be given by taking the magnitude of the plane vector times the cosine of theta I plus the magnitude of the plane vector times the sine of theta j. The magnitude is 400 knots. But theta is not 20 degrees. Theta is 290 degrees. So you're going full 270 plus 20 more is 290 degrees. Then the velocity of the plane is given by 400 times the cosine of 290 degrees, I, plus 400 times the sine of 290 degrees, j. Make sure your calculator is in degrees. Rounding to the nearest whole unit, we get 137I minus 376J. The velocity of the wind is going to be the magnitude of the wind times the cosine of theta I plus the magnitude of the wind times the sine of theta j. The magnitude is given by 50 knots. And theta, again, it's not 30 degrees. Starting at the zero axis down, it's 270 minus 30, which is 240 degrees from 0 degrees. Then the velocity of the wind is 50 times the cosine 240 degrees I plus 50 times the sine of 240 degrees j. The wind velocity is then given by negative 25I minus 43j, rounding to the nearest whole unit. The true velocity is given when you sum these, but the true speed is the magnitude. So we first have to sum vectors p and w to get their resulting vector, and then we need to find the magnitude of that vector. Vector p is 137I minus 376j plus vector w, which is negative 25I minus 43j. The resultant vector is then 137 minus 25, which is 112I, and negative 376j minus 43j is minus 419j. Finding the magnitude, I'm then going to square root 112 squared and negative 419 squared. (112 squared is 12,544. Negative 419 squared is negative 419 times negative 419, which is positive 175,561. That is then the square root of 188,105, which is a true speed of 434 knots rounded. In order to find the bearing, I'm going to take the inverse tangent and consider what quadrant I'm in. The inverse tangent of negative 419 over 112, which is the b value over the a value, gives me a theta of about negative 75 degrees. 112i minus 419j is in the fourth quadrant. And in order to find the bearing from the north-south line, right now I have a theta of negative 75 degrees. That's going from the x-axis down negative 75 degrees. The complement of that is then going to give me the bearing, which is 15 degrees. I then have a bearing of going down south 15 degrees and then to the right, which is east. Skill practice 10 asks us to repeat example 10, but change the still water swimming speed and the current. So I'm going to update the information now. Joe enters a triathlon and he has to swim to a buoy offshore and back again, but there's a current that's flowing due west. If he starts at the closest point J to the shoreline to the buoy, in what direction theta does he need to swim east in order to arrive at the buoy with the current pushing him west? Assume that his speed swimming in still water is 2.5 miles per hour. What is his true speed? First of all, we want to know what the angle is that Joe is swimming. Well, vectors c and v added together sum to the resultant vector that's drawn in blue. This resultant vector has no a component, it's just b. It just goes straight up. And so the a component is 0, which means I can use the fact that the resultant vector is the sum of c and v to help me try and solve for theta. Replacing the vectors with the information we have, I want to find theta, and theta is attached to sine and cosine, both I and j. But I can use the fact that they sum to either 0i or kj, depending on the pieces I want to use. Setting 2.5 sine theta j equal to kj is not going to help me because of that variable k. But if I take the I components and set them equal to 0i because they must equal, the sum must equal 0i, I can use that to solve for theta. That means that negative 0.5i plus 2.5 cosine theta I has to equal 0i. Let's add 0.5i to both sides. I then divide both sides by 2.5i in order to isolate the cosine of theta. 0.5 divided by 2.5 is 0.2, and I divided by I is 1, which means that the inverse cosine of 0.2 needs to be equal to theta. Using my calculator, I get that theta equals 78.5 degrees, rounded to the nearest tenth of a decimal. That's a first quadrant angle, which is what we want. If you go back to the diagram and look, the angle that we're dealing with is in the first quadrant. Now, Joe's true speed is found by calculating the resultant vector, which is kj. So I can now take the j components and set them equal to each other. 2.5 times the sine of theta times j is equal to k times j. Let's solve for k, but also let's substitute in theta. We know theta now. I can divide both sides by j and get that 2.5 times the sine of 78.5 degrees is going to be my k value. And using my calculator, k is roughly 2.4 miles per hour. That is Joe's true speed. We are given the magnitude of three different vectors, and we want to know what the resultant force vector is in terms of I and j. The resultant vector, r, is going to be found by summing the three different vectors that we have. So force vector 1 plus force vector 2 plus force vector 3 is going to give me the resultant vector. I find each of the force vectors using the angle that's given and the magnitude. The magnitude is listed in the given information, and the angles need to come from 0 degrees. So looking at the drawing we have, angle F1 is not listed, but that's because it's straight up, which is 90 degrees. So theta 1 is equal to 90 degrees. F2 from the 0 axis is 90 plus 68 more, which is 158 degrees. The third angle is 360 shy 40 degrees. So if I took 40 degrees away from 360 degrees, I would get the 320 degrees, that is theta 3. Let's find our individual force vectors first by taking the magnitude of the vector times the cosine of the theta, I, plus the magnitude of the vector times the sine of theta, j. Force vector 1 is then 32 cosine 90i plus 32 sine 90j. From the unit circle, I know that the cosine of 90, or the cosine of pi over 2, is 0, and the sine of 90 is 1, which means that force vector 1 is 32 times 0, I, and 32 times 1, j, or just 32, j. Force vector 2 has a magnitude of 24 pounds, an angle of 158 degrees, with my calculator in degrees, I get that force vector 2 is equal to negative 22.3 I plus 9j. Force vector 3 is 15 pounds with a theta angle of 320 degrees. Force vector 3 is then 11.5 I minus 9.6 j. The resultant vector is then found by taking the sum of the I components plus the sum of the j components, or negative 22.3 I plus 11.5 I plus 32j plus 9j minus 9.6j, which is negative 10.8 I plus 31.4j.